No? Well, then I'll call on the next speaker, which is Ivan Aguillo, who will speak on loop quantum cosmology and the cosmic microwave background. Thank you.
Well, thank you for giving me the chance to speak here. It's a real honor. You know, I am originally from Spain, so today I don't want to talk about soccer or football, so I will focus on quantum cosmology. So what I want to do today is, the goal of my talk is to use quantum gravity to push the boundaries of our understanding of the early cosmos. But you know, this is already confusing, because what do I mean by quantum gravity? We don't have any single, complete, self-consistent proposal, and you are right. So what I should write here is to use a proposal for quantum gravity, and one that goes under the name of loop quantum cosmology. But you know, precisely because we don't have any complete theory, any framework that we use must be based on assumptions and physical input, and this is not a counterexample. So what I want to do is to show an example, one example, thank you, of how, by using well-motivated assumptions that I will try to identify during my talk, physical input and approximations, one can build a quantum theory of the cosmos. And then how one can use this framework to address some of the open questions in cosmology. You know, how is the space-time geometry described before inflation in the Planck regime? What happens with the Big Bang singularity? How the familiar notion of time and quantum field theory emerges from first principles, etc., etc. And then I want to use this mathematical framework to make some contact with predictions, with our universe that hopefully can help us to test the main ideas. Of course, you know, I will give you only a brief overview. I only have 30 minutes to summarize the work of several hundreds of papers, but I hope I will be able to communicate at least the global picture. And in particular, you know, I will try to emphasize how non-trivial is, in my view, to go from, you know, from abstract mathematical techniques of quantum geometry all the way down to make contact with observations. So my talk has three parts. I will start talking about what loop quantum cosmology is and how it describes the homogeneous geometry of the universe. And then I will include perturbations on the framework. And finally, I will try to make contact with the CMB. And for more details, I refer you to the session QJ3 that will take place on Thursday afternoon. So let me start telling you a little bit what loop quantum cosmology is. But because this framework is based on loop quantum gravity, let me just dedicate a few words to tell you what loop quantum gravity is. You know, this is a framework for quantum gravity that is based on Ashtekar's reformulation of general relativity using connection variables. You know that gravity, the gravitational degrees of freedom, can be encoded in a metric tensor, but equivalently, one can also use connections to define GR, to describe GR, in particular a SUU connection and the conjugate variable. So this is like the gravitational analog of the vector potential and the electric field of standard electrodynamics, and they are called Ashtekar variables. And they have some advantages compared to metric description. First of all, you know, now the phase space of general relativity is precisely the phase space of a Young-Mills theory. So we have a unifying framework to describe all interactions of nature. And this allows to import techniques of Young-Mills theory to quantize gravity. And second, the GR constraints simplify significantly, and this alleviates a major problem to quantize gravity. Of course, quantization is not trivial at all. And you know, I don't want to go into the details, but just let me tell you that one essential ingredient, key ingredient that people use to quantize this theory, to look for a quantum representation, is to impose strongly the symmetries of gravity, diffeo invariants. And the result is a beautiful and powerful theorem that tells you that there is only one way of doing this. So when, by imposing different invariants, obtains a unique kinematical Hilbert space, which is invariant under this B group, and this Hilbert space is made of functionals of the connection and describes, quantum gravitational fields. And the result is just a quantum geometry, and physical observables like areas, volumes, etc., have discrete spectrum. The next step is to obtain dynamics in this theory, and that must be done through the Wheeler-DeWitt equation, the Hamiltonian constraint. And this is a very non-trivial and difficult step. And part of the difficulty is because mathematical ambiguities are so large that sometimes it's difficult to know which choices are physically meaningful. But this is where what motivates us to focus just on cosmology. And that brings me to loop quantum cosmology. Loop quantum cosmology is a mini superspace version of loop quantum gravity. And that means that you first, at the classical level, focus only on gravitational configurations that have the symmetries of cosmology, and then quantize them, only them, using loop quantum gravity techniques. Of course, imposing the symmetry before quantization simplifies a lot the system, and most of the ambiguities can be removed or solved by physical arguments, and one can, in fact, complete the quantization program and create a quantum theory of the cosmos. Of course, simplifications always come together with limitations, and we should worry about the fact that, freezing the degrees of freedom before quantization may suppress some important effects. But, so if you want, this is the main approximation, the main assumption in the whole approach, and we should keep an eye on that. But history tells us that symmetry reduction is a good guide for physics. But we will keep an eye on that. So let me focus first on the simplest cosmological models, homogeneous and isotropic FRW. Classically, as we normally do in primordial cosmology, we assume that the matter content is dominated by a scalar field, and gravity is just described by the scale factor and the conjugated variable in metric variables. In connection variables, we have the connection, C, and the conjugate variable, P. P has the information of the scale factor, and the connection has the information of the Hubble rate, the conjugate variable. Now, again, we use diffeo invariants to pick up a Hilbert space of quantum FRW geometries. The diffeos are much more restrictive than before, because we are now dealing with a concrete system, but there are still enough residual diffeos to do the job, and they provide a kinematical Hilbert space. And in that Hilbert space, one can, again, obtain dynamics imposing the Wheeler-DeWitt equation, which, when you write it explicitly, takes this form, where, this partial phi is just the kinetic term of the scalar field, the conjugate momentum square. And this is just the part of the Hamiltonian having to do with gravity, with the geometry. And I don't write explicitly here because it's quite long. And this is where we have to extract dynamics from. But you know that in gravity, there is no time. Gravity is a timeless theory, so we need to face the problem of time. But here, this equation already suggests a physical approach, which is, if we take phi itself, the scalar field, as a time, this equation looks like a Klein-Gordon equation, where this will be the spatial Laplacian, and this is the time part. So this equation suggests to use a relational time approach, a la Leibniz, if you want, and describe how gravitational degrees of freedom evolve relative to matter degrees of freedom. And in my opinion, this is probably the most physical way of making time to appear in gravity and in quantum gravity in particular. With that viewpoint, one can solve this equation. This equation is solvable both numerically or analytically, and one has a space of a Hilbert space of FRW geometries, and one can build physical observables on it, and therefore one has a quantum theory of the cosmos, a quantum theory for FRW universe. Whether this theory describes our universe or not is precisely what we want to investigate. So let me just mention quickly a couple of important consequences of this framework. The first one is that one can prove as a theorem that all physical observables, for instance, curvature invariants, energy density of matter, pressure, etc., all of them are bounded from above. That means that there is no observable that blows up in the Hilbert space. So this is the mathematical statement that there is no Big Bang singularity in this theory. More concretely, the energy density of matter is bounded by a fraction of the Planck scale. The Ricci scalar is also bounded by a fraction of the Planck scale. And this is a quantum phenomena. You can see h bar sitting here in the denominator. So the singularity is not avoided because we introduce some exotic matter or something similar. It's the purely quantum gravity, the quantum geometry itself, that makes the rho to have an upper bound and not to go to infinity. If you want, this is similar to what happens with the hydrogen atom, that once you introduce h bar in the problem, the energy density is bounded below. The next interesting result is that all states in that Hilbert space go through an instant, in this internal time, of minimum volume and maximum curvature. So that is a bounds. So one finds that in this quantum theory, that is based on demanding diffeo invariance very strongly, and therefore the Hilbert space is different from the Wheeler-DeWitt Hilbert space. One finds that the Big Bang singularity of GR disappears and is replaced by a bounds, by a quantum bounds. This quantum bounds can be thought as a quantum bridge that joins two classical phases of the universe, one contracting and one expanding. To give you some extra intuition about, about the geometry, because this is a quantum theory and sometimes it's difficult to get intuition, let me consider the example of a concrete situation in which I choose a quantum state for the geometry that is very sharply peaked in the variables. So the quantum dispersion, the relative quantum dispersion is very small. I want to consider this peculiar family of states because for them, they are semi-classical. I can neglect higher order corrections, and that will give you some extra intuition. For them, it happens that the geometry, the quantum geometry, is very well approximated by a smooth metric tensor, like in classical GR. However, that smooth metric tensor, that I will call the effective metric, doesn't satisfy Einstein equations, but rather satisfy some quantum-modified Einstein equations, where these red factors are the quantum modifications. And we can get some intuition just by paying attention to the Friedman constraint, where we see that this quantum correction becomes very small whenever the density of matter is negligible compared to the Planck scale. So this red parenthesis is 1, and we recover GR at low densities and low curvatures. However, becomes very relevant whenever energy density is comparable to the Planck scale, because this factor becomes 0, so the Hubble rate becomes 0, and rho becomes maximum, and that is precisely a quantum bounds. So it is precisely these quantum corrections that replace the Big Bang singularity with a quantum bounds, and that is very clearly seen here in these effective equations, which are only valid for sharply peaked states. So just a few words about that this work has been extended to more complicated geometries with curvature, with cosmological constant, with anisotropies, and even inhomogeneities, Gaudi models. And the relation between loop quantum cosmology and loop quantum gravity has been explored a lot, and perhaps there are some talks about these extensions in the parallel session. This is about a quick summary about the space-time geometry. So what I want to do now is to apply this framework to the early universe. Try to use this mathematical theory to describe our early universe and see what happens. So first, let me tell you that I will use this framework not to replace inflation. You could try, but what I am going to do is to use this theory to complete inflation from a quantum gravity viewpoint. So inflation will be there, and this theory will try to complete it. And this is, if you want, a cartoon of the picture that I have in mind. The universe contracts in the past whenever curvature, invariance, and energy density reaches the Planck scale, quantum gravity effects come into the play and make the universe to bounce. Then, whenever energy density goes well below the Planck scale, quantum gravity effects become unimportant, and we have a classical universe in which there is some pre-inflationary expansion, then inflation appears, and then we have the standard model. So I will use this framework in order to complete the inflationary paradigm. And that brings me to the second part of the talk, because you know that the way that we explore the early universe is through perturbations. They are our proofs. So what I need to do now is to learn how to describe scalar and tensor perturbations in this framework. But the task is not trivial, because you know, in a standard cosmology, perturbations are quantum fields propagating in a classical spacetime, quantum fields in a curved spacetime. But here the spacetime is quantum, so I should learn how to propagate quantum fields in a quantum spacetime. And this is what I'm going to do in this section, or at least summarize. So here I will review one way of doing it. There are others, and you can go to the parallel session in the talk of Guillermo Mena, and you will see other ways of doing it. The results are quite similar, with interesting differences, but in general are quite similar. So what I'm going to show you was worked out a few years back, and is in a series of papers by these authors. Here, I want to start just giving you the flavor, you know, just symbolically what happens, what we do. So our starting point now is a wave functional that depends on both, on background, homogeneous and isotropic degrees of freedom, the scale factor and the background scalar field, and linear perturbations. But remember that in standard cosmology, what allows us to treat perturbations in an easy manner is the fact that they are perturbations. You know, the fact that they don't modify the background, that they are test fields. Because they are test fields, they are just, you know, just quantum fields propagating on a fixed given background spacetime. Here, I want to follow the same approach. So I will assume that perturbations are test fields, and among other things, that implies that the entire wave function can be written as a product of the background part, describing FRW quantum geometry, and perturbations. And furthermore, that perturbations do not modify the background geometry, so back reaction is negligible. Therefore, the background wave function is just the functions that I was describing in the previous section, are just the solutions of loop quantum cosmology. Now, what we have to do is to proceed as in semi-classical cosmology. Choose a background, and then let's see how perturbations propagate on the top of that background. The evolution of perturbations will come out from the entire Wheeler-DeWitt equation, but once I choose a given background, then I can trace out the degrees of freedom of the background from this equation and extract an equation for perturbations. But precisely because this cross product, this trace out is just taking expectation value, because there is a product, so no information is being lost by taking expectation value. And what you get is a differential equation for perturbations in which the coefficients are not classical functions, but are expectation values of background operators on the chosen quantum state. And that is a quantum field theory on a quantum spacetime. Just to be a bit more explicit, just let me tell you that by manipulating this equation, one finds something that I find quite interesting and remarkable, and is that the resulting equation can be written, you know, manipulating terms, in a way that look like the same equations that we use in GR. You know, Klein-Gordon equations for scalar perturbations and for tensor perturbations, in which there is an additional potential for scalar perturbations. But this is surprising because we are doing quantum gravity. So what this box operator is, what is the metric that appears in that box operator? Well, first of all, it's not surprising, although nice, to see that if we choose the background geometry to be sharply peaked, you know, with very small quantum dispersions, the metric that appears here is the effective metric that I was describing you before. But we can go beyond and consider states for the quantum geometry, the FRW geometry, that are not sharply peaked, that they have large fluctuations. Then the metric that appears in this box is given by this couple of complicated expressions. You know, the scale factor to the fourth power is obtained by computing a complicated expectation value of background operators in the chosen background state, and the same for this conformal time as a function of the internal time. I don't want to go into the details, but just let me to emphasize the fact that what we obtain by doing the analysis is that even though the space-time is quantum and may have quantum fluctuations, it's still homogeneous and isotropic, but has quantum fluctuations. Perturbations, precisely because they are perturbations, they cannot see. They are not sensitive to all this information in the quantum state. They are poor proofs of the space-time. They can only fill a couple of quantum moments of the background geometry, and those quantum moments make them to believe that they are like in a classical universe, or in a smooth metric, not classical, sorry, in a smooth metric. So for perturbations, they don't realize that the background is quantum, and they propagate in a smooth metric that, of course, contains h bar on it. And I find this quite remarkable because one can see explicitly how a quantum field theory on a fixed, smooth background emerges from this quantum gravity theory. So at the practical level, if you want to evolve perturbations in loop quantum cosmology, you have to choose a quantum state for the geometry, compute these two expectation values, and from that on, proceed as in standard cosmology. And if the quantum state that you choose is not, is not wild, is relatively sharply picked, then if you use the effective equations I was showing you before, you will get an excellent approximation. So use these effective equations, solve them, which is as difficult as in GR, and then use just these equations to propagate perturbations, which is equivalent to what you do in semi-classical gravity. Of course, to get to these results, one has to prove it, and this is precisely what we did. Okay, so let's now try to apply this framework to describe the early universe. Now we know how to describe the background geometry, perturbations on it. Now we can apply it to describe physics. So let me summarize the strategy. First, let me refresh your memory about what we do in standard cosmology. In standard cosmology, we start the evolution at the onset of inflation, and we assume that perturbations start in the vacuum state, and we evolve them across inflation. They acquire some features, and the result is imprinted in the CMB. But now we have a complete spacetime, so there is no reason to start the evolution in the middle. So we follow the same strategy, but perturbations will start in the vacuum in the far past, and they will be evolved across the bounds, across the pre-inflationary regime, and they will reach the onset of inflation, but precisely because the evolution across the bounds will excite perturbations or modify perturbations in such a way that they will reach the onset of inflation in an excited state, not in the Banks-Davis vacuum. The excitations will be a consequence of the evolution across the bounds, and they will be imprinted in the CMB, and those imprints are therefore a window to see, a window to the pre-inflationary universe and a window to the bounds. So this is the strategy that we will follow, and I want to show you quickly the results that we obtained for the two-point function. But before that, let me come back and give you some intuition about what we can expect. What we can expect is the following. It is not difficult to understand that what the bounds is doing for us is introducing a new physical scale in the problem, whatever scale characterizes the bounds. For instance, the curvature radius. This is the new scale that the bounds is given for us, or the Ricci scalar, or whatever you want, any of these scales. And it is not difficult to understand that, if you consider a perturbation, a Fourier mode of scalar or tensor perturbations with a wavelength which is much shorter than the curvature radius of the bounds, than the radius of curvature, this perturbation will not fill the bounds because, will be too energetic to fill the curvature. It will propagate as in Minkowski spacetime, and that perturbation will reach inflation in the vacuum state. On the contrary, if you consider a long wavelength perturbation, that will fill the curvature and will be excited by the bounds. So roughly speaking, we expect that the bounds is going to modify the infrared sector of our CMB and not the UV because perturbations which are very ultraviolet essentially will not fill the bounds. This is just to give you some intuition about what is going to happen. So let me show you the results for the power spectrum. This is just quickly. More details will be given in the parallel sessions. So let me show you the results for the scalar and tensor power spectrum. They are very similar to each other qualitatively, so let me just focus on one of them. Gray points, so this is the power spectrum as a function of the wave number. Each gray point is the numerical result for a concrete value of k, and the black line is the average of the gray points with some binning. You know, let me just zoom in this plot so we can see it better. So here, where I have this red line is the predictions of standard inflations with Banks-Davis vacuum, just to compare. And what we see is precisely what and this line, this vertical line, indicates this new scale that the bounds introduces, you know, the scale of the bounds. And what we see is precisely what we were expecting. For UV modes, you know, larger wave numbers, shorter wavelengths, the power spectrum agrees with inflation. The bounds is doing nothing. However, for more infrared scales, the bounds is modifying significantly the power spectrum. So the main message is that the pre-inflationary evolution, the bounds itself, modifies the power spectrum for infrared modes compared to the new scale. Of course, the million-dollar question is which part of this plot we can see in the CMB, which is the range of modes that are visible in our CMB. Some of them will be too small, we cannot see them. Some of them will be super Hubble, we cannot see them either. Well, it is not difficult to understand that the range of modes we can see here will depend on how much expansion there is between the bounds and today. If there is a huge amount of expansion, the effects from the bounds will be redshifted to super Hubble scales, and we will be observing just this part, you know, my left part of the plot, the part that agrees with inflation, and we will see nothing coming from the bounds. In the contrary, if the expansion is not too large from the bounds to today, then we could possibly see some part of the effects from the bounds. But it happens that the amount of expansion is a free parameter, depends on which background spacetime we choose. So there is a free parameter in this theory that tells us which part of this spectrum we can observe. And I think there is a parallel session today in which there is some more information about this free parameter. In summary, for large post-bounds expansions, the predictions are the same as in the standard inflation. But that is kind of nice, because then one obtains just a quantum gravity extension of the inflationary scenario. You have inflation extended to the past, the Big Bang singularity is absent, you can face Transplanckian issues because you have a quantum theory, inflation emerges out of the bounds in a natural manner, and the predictions would be the same. So it's just a nice extension or support to the inflationary scenario. On the contrary, if the amount of expansion is smaller, we may have some quantum gravity corrections at large angles in the CMB. And the most important ones is, as I said, a modification of the power spectrum. The spectral indices and runnings get modified. There is a reduction of the tensor to scalar ratio, and also a modification of the consistency relation. And I refer to you to more talks in the parallel session for details of these results and more. So quickly, let me go beyond the 2-point function and talk about the 3-point function, the non-Gaussianity. There is a talk dedicated to this on the parallel session, and I refer you for the details there. So why do we want to study non-Gaussianity coming from the bounds? For 2 reasons, at least. The first one is that, if non-Gaussianity is too large, remember non-Gaussianity is the next to lead in order. It's just self-interactions between perturbations. If they are too large, the perturbative expansion that we have used may break down. That will tell us that perturbations are not perturbations. The fluctuations on them are huge. And this is a real possibility because, self-interactions between perturbations become effectively strong, close to the Planck scale. So it is possible that perturbations get strongly coupled in the early universe. So one has to check that. And second, even if perturbation theory happens to be okay, there are strong observational constraints on non-Gaussianity coming from Planck. So if we violate them, this is ruled out. So therefore, we need to check both things, A, to make sure our theory is self-consistent, and B, in order to claim compatibility with current observations, and also to see if we can predict some extra effect. So the goal here is to compute the three-point function of curvature perturbations, co-moving curvature perturbations. They are given by the bias spectrum, except for this Dirac delta that tell us that the three wave numbers must form a triangle. So what we need to do is to go beyond linear perturbation theory, so expand the Einstein action at third order and quantize that. For inflation, was done by Maldacena in 2003 and was a hard calculation. Here it's even harder because we don't have the slow roll approximation, neither a quasi-de Sitter geometry to provide analytical approximations. So one has to face the full calculation and try to solve it. So we have done it numerically. We have developed a numerical code using the class infrastructure. Our code is publicly available in this link. And it is not suited only to loop quantum cosmology, it is suited in general. So if you want to compute non-Gaussianity out of a slow roll, quasi-de Sitter space-time, etc., you can take advantage of it. So I'm going to parameterize, as usual, non-Gaussianity by this function FNL, that depends on 3 wave number. And FNL is defined from the bias spectrum by just this equation, where these deltas are just the power spectrum with dimensions, the dimension-full power spectrum. So FNL, intuitively, is just the bias spectrum in units of the square of the power spectrum. So let me first show you what we obtain when FNL, when we put the same K, K1 equal to K2 and equal to K3. This is called the equilateral configuration because the triangle is just an equilateral triangle. So this is what we obtain for FNL, and this is just the absolute value. And we see, that this flat shape for UV ultraviolet modes, and then this strong enhancement up to 10 to the 3. Again, this is just the absolute value. So you can see that FNL is very oscillatory and grows in amplitude a lot. The same happens if you choose different configurations. Here I show you different configurations, and the same happens, and we have checked that for many other configurations, this is the typical shape. So just let me put the power spectrum close to it so we can compare. So again, the red line is the inflationary result, the standard slow roll inflation with Banks-Davis initial conditions. And this vertical line is the new scale that the bounce introduces. So the qualitative understanding is the same as for the power spectrum. UV modes do not fill the bounds, and for the bounds do not create further non-Gaussianity. The result, the same as in inflation. But modes which are comparable to the new scale, the bounce creates a lot of non-Gaussianity and boosts FNL up to values of the order of 10 to the 3000. So the message is that the bounce amplifies non-Gaussianity significantly for modes that are of the same order or more infrared than the curvature radius at the bounce. And because this new scale, now the resulting non-Gaussianities are strongly scale-dependent, in contrast to many other models in the market. So this is the feature, the key feature of the bounce, this new scale and both power spectrum and non-Gaussianity strongly scale-dependent. So you will see more details in the parallel session, but just to tell you that non-Gaussianity happen to be peaked, are quite homogeneous, but happen to be peaked in a squeezed, but not too squeezed configurations. So just to summarize, the results of a standard inflation are exactly recovered for UV modes, and that is a good check. Non-Gaussianity is very oscillatory. The amplitude grows a lot for infrared modes. And we have checked that the perturbation theory is still under control. FNL grows by several orders of magnitude, but the power spectrum is still small enough to make these new corrections to be quite smaller than 1. So perturbation theory doesn't break down. Comparison with observations. So we know that the Planck satellite tells us that the non-Gaussianity are very